Happy Friday. Today is Feb 12th. The daily quiz that you guys should be working on for today is the daily quiz number 6 on Gradescope. A few questions, pretty quick to finish. So please make sure that you complete that. Homework that you guys are working on. Homework 3 is posted. It's due on Gradescope on Tuesday, Feb 16th. The next homework 4, will be posted early next week. So I'll post it on Sunday or Monday so that you guys can get a head start on homework 4. The studios that are due. For Studio 1, again, both the TA checkoff and the studio report is required for each studio submission. Studio 1 is due next Wednesday. So Feb 17th is when Studio 1 is due, and it's an individual submission. Studio 2 is posted now, and some of you have already started working on it, completed it, got checked off on it. So all that is good news. It is due the following Wednesday. So for Wednesday, Feb 24th is when Studio 2 is due. And then Studio 2 is actually the first studio in which you are allowed to do a team submission. So team of 2 students. Questions or concerns about things that are coming up? 1, 2. Okay, so today we are going to be talking about Boolean algebra. This topic tends to be a little bit dry, maybe boring at times. So I'm going to try to kind of keep it interesting for you guys. And, I'll try to look at Boolean algebra from different angles. I love what? All right, so let's in general. So I know students who think that this is dry. Well, I thought of it as a dry topic when I learned it. But when we are going to go through these properties, I'll try my best to I'll try my best to keep it interesting for you, so that you get the most out of this discussion. All right, so let's start with an example here. We have a situation with 2 inputs. So let's say you have a 2-input gate, right? This gate could be any logic gate. So if you have 2 inputs and these are 2 binary variables, x and y, and they are both functioning as an input in this case, if you have 2 of them, then your outputs, the possible outputs that you can have for this particular logic gate are 16 in number. And the reason why they are 16 in number is because each of these outputs could be 0, 0, 0, 0 or 0, 0, 0, 1, all the way up to 1, 1, 1, 1, right? So these are all possible outputs or possible unique functions that you can have in the context of a 2-input gate. And you can clearly see that if you had a 3-input logic gate, for example, with inputs x, y, and z, then the possibilities will keep on increasing exponentially, right? So from 16, you would jump to 32 and so on. So, would you jump to 32? How many possible functions will you have if you had x, y, and z? So if you have x, y, and z, the number of rows in this table would be not be 4, it will be 8, right? So if there are 8, then the possible number of functions would be the 3 inputs. Unique functions, how many unique functions can you have? Not going to be 32. It's going to be 2 raised to 8, right? You're getting 16 because they are 4 rows. You guys see that? So 5 is 32, 64, 5, 6, 7, 8, right? So you have 32, 64, 128, 256. So 256 functions in this case. Yeah, that's right. 256 unique functions you are going to have when you have X, Y, and Z as your 3 input gate. So clearly you are getting a lot of uniqueness as you go from 2 input to a 3 input situation. Now, each of these functions, f0 all the way to f15, is right now indicating an output binary variable, right? So f0 is one output, f1 is one output, and so on. And it is related to the two inputs x and y by some logic function, by some unique logic function. And they're all going to be unique, right? It's going to be all different. So for example, if you look at f0, f0 is independent of x and y, right? f0 is always 0, no matter what x is, no matter what y is. So if it is 0, independent of x and y, you see that logic function simply be f0 equals 0, a false. And then you can have f1 equals 1, which is, it is a 1 here. So that means that only when x is 1, y is 1, you have f1 equals 1. So that gives me the logic gate of AND. F3 is simply the same as logic, the input variable x. So f3 in this case is x. f5 is y. And you have a total of 16 of them. You see an AND gate play out in f1. You see an OR gate play out in f7. You see inverters for x and y separately play out in f10 and f12. But if you now, let's try to take a look at f8 and f14, right? So f8 is a one unique function that results from the logic gate between x and y. And based on the table here, it is saying that when x is 0 and y is 0, in fact, only when x is low and y is low, output f8 is high, only in that situation. So this is f8 is sort of the opposite of f1, right? So f1 has 0, 0, 0, 1. F8 opposite of, no, f8 is opposite of f7. That f8 right here is kind of the exact opposite of f7. So when you had 0, 1, 1, 1, f8 has 1, 0, 0, 0, exactly the opposite. So if this was OR, this would tell me that this is a NOR function, right? So that's what you have over here. A NOR truth table for two inputs x and y. Output is, we are calling it z, which is kind of the same as f8 in our case. The output is high only when both inputs are low. The symbol for that, an OR gate followed by a bubble. The OR gate is your logic function and the bubble signifies the inversion in this case. Yeah. So OR followed by bubble. Right. So that's your NOR. And now if you look at F14, F14 turns out it is the exact opposite of F1. 0, 0, 0, 1 is now F14, 1, 1, 1, 0, exactly the opposite. So if this is AND, this is actually NAND, right? So the truth table for that guy is indicated over here. Z is low only when both inputs are high. The symbol for that is AND followed by a bubble. Again, AND is your AND logic function and the bubble is your inversion. And we looked at, you know, the transistor level design for these functions. And we said, yeah, NOR and NAND, they are really good. They are going to be able to do the job with fewer number of transistors. So we prefer NAND. We prefer NOR. In fact, to get AND and to get OR, we actually need NAND and NOR, and then we invert that. The last function over here, F15, again, independent of x and y. It is simply 1 all the time. So we can say F15 equals 1, right? So in some cases, it is directly dependent on the input. And in some cases, there is a gate between them. And in some cases, it is a constant, 0 or 1. Now we can also have logic functions. We can add 2 more logic functions to this list. So far we have been talking about not, buffer, or, nor, and NAND. Now we have exclusive OR and exclusive NOR. And there is a usefulness to having these logic functions. The bad news is that it is actually a compact representation of logic gates. It is not another, like a new NAND gate, right? It's just a way of representing in a compact manner. So if you look at exclusive OR, it is actually an inequality detector or a difference detector. Well, how do you know that? Well, exclusive OR means what? Let me write exclusive OR in this way. So exclusive OR, XOR. Is it okay if we used exclusive OR in homework 1? Are you talking about the full adder? Sure. Go ahead. Yeah. Homework 2. Yes, you're right. Yeah, you can use exclusive OR. There are many ways of expressing that full adder logic expression. Now let's come back to exclusive OR. What is the symbol? Well, you have a OR sign, and then it is inside a circle, right? That's your exclusive OR operator. But it is actually made out of some basic gates. So for example, over here we have one AND gate to do that. We have one AND gate to do that. We have one NOT gate to do that. We have one NOT gate to do that. And then we overall need to do an OR operation, right? So we actually need two input AND gates, two NOT gates, and then one 2 input OR gate to get that done. Isn't exclusive NOR the biconditional? So exclusive NOR is an equality detector. It is going to give us a true input when things are the same at the input side. So if well, let's come back to that in just a second. So exclusive OR, the main purpose of exclusive OR logic function is to check for inequality between the inputs. The now, or the difference. When you look at exclusive NOR, which is exactly the opposite of exclusive OR, this checks for equality. Right? So X and Y, if they are representing two input binary variables, if they are the same, then the output of this exclusive NOR gate will be high. So it's an equality detector. And exclusive OR and exclusive NOR logic functions are very useful in the design of comparators. Now in Studio One, you guys designed a comparator that was sort of based off of basic gates, right? And, or, and not. However, if you looked at the exclusive or exclusive NOR, it would have been very convenient to go through that comparator. So later in the series of lectures, we will have, when we start looking at very interesting combinational circuits, we will look at a comparator. And we'll try to build an 8-bit comparator or a 4-bit comparator. In which case we will start using exclusive NOR to do this. Now, Andrew, I don't know if you want me to look at the link or not. I'm not sure. Okay, it's an image. Let's see. True, false, false, true. Yeah. So this is your It's a virus, don't open it. Well, too late. You will be flagged by the CIA. I would be honored to be flagged by the CIA. All right, let's. I know you guys are in a pretty good mood today. That's a good sign. Let's try to do this. Exclusive OR. It's related to the gates. And how did you get this? Well, I looked at the truth table to get that done. What is the symbol? It's an OR gate, and in front of that there is an additional arc. That's how you know. That's how you distinguish between an OR symbol and an exclusive OR symbol. Again, like I said, this is just a compact way of representing a bunch of basic gates. In fact, later on, we'll try to see that you could actually implement an exclusive OR function using just NAND gates. And we could also do that by just using NOR gates. We would be more interested in doing that as opposed to using basic gates. Now, for exclusive NOR, the situation is exactly the opposite, right? So it's an equality detector. So X exclusive OR Y, and the entire thing gets complemented. That's your exclusive NOR. And over here, you are checking for equality, X and Y, or X complement or Y complement, which essentially means that this particular term over here is going to be true when both inputs are 1. And then this particular term is going to be true when both inputs are low. So it checks this or that. It checks whether both are 1 or both are 0. Right. So what is the symbol? Well, it is exclusive OR followed by that bubble, which signifies inversion. Right. So that's your logic gate symbol for exclusive NOR. Next, there are truth tables, which are essentially related to the logic expressions. You have X and Y as your two input binary variables. Z is your output variable for the exclusive OR. So when X and Y are the same, you get a false output, 0. And when X and Y are not equal, it's an inequality detector. When X and Y are different, you get a 1 or true out of this. Now, using this table, you can actually write the expression for Z, right? Z is true in two situations. One is right here, the other is right here. So for the first guy, you would say X has to be a 0 and Y has to be a 1. Or the second situation is X is a 1 and Y is a 0. Right? So this actually takes you back to how this was written, the logic function. And the same way, if you do that for this particular truth table for exclusive NOR, you would get that logic expression. So for exclusive OR, we have seen how it is written in its compact form. How is it written using basic gates? What is its symbol? What is its truth table? So what is its property, right? It's checking for equality or checking for inequality. Very useful for comparators design. Next, let's come to useful laws or theorems of Boolean algebra, right? What is the definition? The dual of a Boolean equation is derived by replacing AND operations by ORs, OR operations by ANDs, constants zeros by ones and ones by zeros. But we are going to leave literals unchanged. What does a literal mean? A literal simply means a binary variable that is involved in your logic expression. In this case, it's going to be a logic equation, right? So X in this case is a literal. Let's see, it also looks like Y inverts X or exclusive NOR, exclusive OR if it's a 1, which seems useful. Yes. So there are other things that exclusive OR and exclusive NOR can be used for. So you can do a conditional, like a complementing of one of the variables. So you not just for exclusive OR, exclusive NOR, you can apply this for other gates, right? So NAND and NOR might have certain useful properties too. So you're absolutely right. It can be used to complement a variable or pass one of the variables through if one of the other input is true or false. So absolutely. Next, we are talking about the principle of duality here. So what is the principle of duality? Well, if you have a heads, then the other side is going to be tails, right? So if you have a Boolean equation which is true, then its dual will also be true. That's your principle of duality. Let me write that statement down quickly here. Principle of duality. If a logic equation or Boolean equation is true, then its dual will also be true. What is a dual? Well, if you want to find a dual, then you have to do all of this. You have to replace AND with or with AND, zeros with ones and zeros. However, you cannot change the literals, meaning you cannot do X and over here X complement, right? So you have to leave the literals the same, no matter how many they are. In this case, let's see, all of these properties 1 through 5 have only one literal, right? X is your literal. Let's try to see these properties first. These are Boolean algebra properties. Some of them are going to be the same as arithmetic algebra properties, but a lot of them are going to be different from arithmetical algebra properties. So you got to be careful about that distinguishing factor there. All right. X or 0 is X. That's your first property. This is not arithmetic sum. That is your logical OR operation. 0 is your false, right? So if I take a binary variable X and I OR it with 0, then I get the same binary variable X. That's your property. And the dual of that is represented as 1D. You see, you're taking X, leaving the literal as is. The operator OR is now dual of that is AND. 0 is changed to 1, but the last one is a literal which remains unchanged. So if you start with a true statement here, then principle of duality says that 1D also should be true. In other words, if you prove 1, then 1D is proved, right? So that's your principle. Now, there are very interesting ways of kind of proving these properties, and so let's take a look at ways in which you could prove Boolean algebra properties. So I'll just list them down over here. Ways to prove Boolean algebra properties, BA properties. So from here on out, you will see me refer to Boolean algebra as BA. That I'm referring to Boolean algebra. So the first way of doing this, let me start with the easiest way of proving things, which is the perfect induction method. Perfect induction, also called as the truth table method, and that's your easiest way of doing it. And the reason why it is easy to prove things using truth tables or perfect induction is because it is structured. Like there's a process, there's a procedure, you follow it, write the truth table for the left hand side, write the truth table for the right hand side, compare them. If they match, you have proved it. So it's very methodical, which is why I say that it is the easiest way. The next one is using Venn diagrams. And if you have learned set theory, then you may have come across Venn diagrams. It's a very graphical representation of sets. We can use Venn diagrams over here, and they translate pretty well because for Boolean variables, you have true and false, right? 0 and 1. And for Venn diagrams, you have those two states. You have shaded part and the not shaded part. So it translates very well, and we can use that to prove the Boolean algebra properties. So we'll try to learn that here as well. The last way here I'm going to say, which is probably the most difficult of them, is to use other Boolean algebra properties. Right. So if I've already proved a few of the Boolean algebra properties, then I can use them to prove the following ones. Right. So I can use the previously proved ones to go ahead. So I hope you guys now get the list of ways, and we will try to kind of get a good sample of each of these ways while we are going to go through this list. That's the goal. So the first way, so some of them are going to be pretty straightforward, right? So let's say I want to prove 1, right? So if I want to prove 1, x or 0 equals x, let me use the perfect induction method to do this. So I'm gonna keep adding pages here. So for property number 1, I'll say the property is x or 0 equals x, where x is a binary variable. So the moment we say x is a binary variable, in this case, what are the values of x that are possible? Zero and 1, right? So x can take a value of 0 or it can take a value of 1, right? So if I try to prove this, I can start with my left-hand side of the equation, which is x or 0. So let us see what is left-hand side. I have x or 0. And you guys said x can take the value of 0 or 1. That's it. Those are the two values that are allowed. So let me say what happens when x is 0 and when x is 1. So I have those two possibilities to consider, 0 or 0 and 1 or 0, right? Because x can only take the value of 0 or 1. So what is going to be this and this? Now we know the truth table of a OR function, right? Both inputs, one of the inputs has to be true in order for output to be true. So 0 or 0 will give me 0. 1 or 0 will give me 1, right? So looks like this guy matches this guy exactly, right? Which means if this was used to represent a variable x, then this has to represent the same variable x, right? So that's how you would say x plus 0 or x or 0 equals x. That's how you would prove it, right? So this is equal to right hand side, and that's how you would prove it. And we call this perfect induction method. So perfect induction essentially means that you are going through each possibility for x and you are comparing whether you prove that or not, right? So you are working through each possibility. And I hope you can relate that to truth table, right? That's what a truth table does. It lists out all the possibilities and evaluates the function for all those possibilities. Perfect induction. Okay, next. I guess I don't need to prove 1D because of principle of duality, but just let's quickly go through that. What is the property? The property is x and 1 equals x. The proof would be what? Left hand side. Consider left hand side, x and 1. Two possibilities for x, 0 and 1, and 1 and 0. In both these situations, I'm going to get low. And do I have 1? Oh, this needs to be 1. So I have 0 over there and 1 over there, right? This guy matches this guy. Here, this guy matched this guy. So this should be evaluated as x. 0 and 1 is 0. 1 and 1 is 1. X and 1 should be x. All right. Questions about these two properties, 1 and 1D? We are using the first way of doing it, and I claimed that it was going to be easy. So I hope that you are in agreement with that it is easy to prove using perfect induction or truth table method. Let's go into property number 2, right? So property number 2, what do we have? We have, let me go back to my list here. We have x or 1 equals 1. So x or 1 equals 1. Sure, that makes sense. If I don't really care about this variable because one of these conditions was true, so my output should be true, right? So this can have the value 0 or 1, and when x is 0, we have x plus 1 equals 0 plus 1, which equals 1. And when x equals 1, 1 or sorry, x or 1 equals 1 or 1 equals 1. And then we simply compared. This was our right hand side, right? So for both values of x, our right hand side worked out to be 1. So slightly different way of working through the perfect induction method. At the core, we are still using perfect induction here. Next property is 2D. X is a literal which should be left unchanged, or becomes and 1 becomes 0 equals 1 becomes 0. Right. So that's your property, and you can check back into your table to make sure that it is the case. And here things are going to be pretty much working out the same way as this with a few changes. So let me copy that, paste it here, and I may have to erase a few things. 0 1, this needs to change, that needs to change, those need to change, that needs to change, that needs to change. Everything else is the same. So when x is 0, x and 0, x and 1, right? And then what do we have here? 0 there, and then 1 and 1 is 1, right? So this x and 0 is 0. When x is 0, you have that. This should be 0. When x is 1, 1 and 0 is also 0. So in both the cases, you got 0. So that is your right hand side in this case. All right, questions, you guys? Now you can probably extend this to say, all right, what is going to be x and y complement and z and 0? What is that going to be? 0, right? So it is going to be 0 over here. And the way we do that is essentially treat all of this as your variable x, right? And similarly, we could use the second property number 2, to say, all right, what is going to be this? Y and z complement or 1 equals what? 1. Because now you're treating all of this as one binary variable. So when you're working through some Boolean algebra properties and based problems, you will often have situations that look more like this. You're not going to have situations that look like this very often. Okay, so let's move on here. Let's go back in my list and see the idempotent law, which is x or x is x, and I have the other version of that, x and x is x. So let's try to prove number 3, and I will do that right here. So controlled inverter. Yeah, that is what I was looking for. So I believe exclusive or exclusive NOR is also a controlled inverter. That is, I think that's what Andrew was talking about earlier, right? So if one of them is a 1, right, when it is 0, it's right. So exclusive OR is also a controlled inverter. Yes. So if you say x is 0, then z equals y. When x is 1, then z equals y complement, right? So you're able to control using x whether the output is the same as input or y or the inverted version of y, right? So again, these gates can be used in interesting ways to accomplish things like a controlled inverter. There is also a controlled buffer. So there are other things that they could be used for. Okay, let's come back here. Idempotent law. All right, sorry about the tangent. I was trying to recollect what it is called specifically. Let's see. X or x is x. Variable is the same variable. All right, let's do this. Another way of doing it. I will have a column for x and a column for x or x. X is a binary variable, so only two possibilities. What are those two possibilities? 0 and 1. So if there are two possibilities, 0 and 1, in the first case I'm doing 0 or 0, in the second case I'm doing 1 or 1. So in the first case I get 0 here and 1 here, right? So this guy matches this guy. Right, so that's proving idempotent law. Do I have to remember all the properties? Probably something that you're asking. No, you don't have to remember all the properties, but you need to understand how to use them and when to use them, right? So during exams and so on, there will be a list of properties that I will make available to you. You can refer back. You can refer to them, right? So you don't need to remember the names or the numbers or the property itself. You will have a cheat sheet for that. The issue will be whether you know which property to use and in when, right? Which property and when. That'll be based off of your practice using Boolean algebra properties. And I'll give you guys a few tricks later on. So that some of the ways you can say, all right, this property is going to be very useful here. Let's see, the dual of this, x and x is x, right? And I suppose the similar proof to 3, right? This is a very similar to proof of 3. If I'm going fast, please let me know. Let's put this here. And over here, got 0 and 1 as my two possibilities. What's dual? The dual is this. The dual of any equation. Let me... Dual of a logic equation. Replace plus with and with plus or 0 with 1, 1 with 0. So if you take an equation and you replace it, from that equation you replace this with this, this with this, this with this, this with this, you get the dual of that equation. All right. Let's see. So that's what we are doing here, right? So 3 to 3D, right? We say 3 is your the property, and then The dual of 3 is 3D. So x, we don't change the literal, by the way. So x is a literal here, which is a variable. We are going to leave that as is. We are simply going to change. In this case, we just change the plus to and done. That's the only change that is required. And the principle of duality says, if you prove the logic function, then you have actually proved the dual of the logic function as well. All right, let's go back here. What do we have here? 0 and 0 equals 0. 1 and 1 equals 1. So x and x should be x. This guy is the same as this guy. Matches. Okay. How are we doing? Let's go to the next one. What is the next one? Involution is essentially saying double negation cancels out. X complement and the whole thing complements equals x. Okay, so that's okay. 2 did 3. All right, let's do that and then do 4. Let's say involution law, which is x complement and the whole thing gets complemented equals x. In other words, double negation cancels out. And you know, you could also see something like this, right? So x complement and double complement, the two complements cancel out. So how do you prove this? Well, let's see. X equals 0, which implies what? X complement is 1, which implies x double complement equals 0. In the other situation, when x is 1, x complement is 0, x double complement is 1. This guy matches that guy. And you know, in the involution law, there is only literals that are involved, so we don't have a dual here. There's no 4D. 5. These are laws of complements. So x or x complement is 1, x and x complement is 0. Let's maybe we can do this using Venn diagrams. Yeah, I think using Venn diagrams this will be good. So let's all right. So for 5, let's use Venn diagrams, and the property is x or x complement is 1, right? That's the property. And because we are using Venn diagrams, I'm going to first denote what is my shaded area representing and what is my unshaded area representing. So when you have Venn diagrams, some parts of the Venn diagrams you shade, and then some parts of the Venn diagram you leave unshaded, right? So when it is shaded, I'm going to say that is representing true in a logic function, and when it is unshaded, I'm representing false or low in my logic function, right? So that's what I'm going to use as my form of logic, the Venn diagram notation. So you typically see what? You see Venn diagrams being a box which represents the universal set. Don't fill with color, please. So a box that represents the universal set. And how do you denote a universal set? You use the Greek letter zeta to denote universal set. Like that's everything in the space. And inside that space, you have a binary variable. How many do you have here? Well, you just have one, right? X. So let us say in that universal set, we have this guy representing X. So X, so let me use this guy for left hand side. And I'm also going to use a similar one on the right hand side. Is this Microsoft OneNote? The software that I'm using? It's actually GoodNotes 5. It's a iPad app. All right. So on the left hand side, what do I have? I have x or x complement, right? So where are things true if I just look at x? So I'm using this guy for right hand side and this guy for left hand side. So for this guy, let us use maybe blue for this. Where should I shade to represent x? Inside the circle. Brilliant. So if I shade inside the circle with blue, I'm essentially saying the variable is true inside this space because that's representing x. The circle inside the circle would be where I would shade for x. And when you do x complement, what are you doing? X complement essentially means everything outside x, right? So for x complement, I would be shading everything but x. Maybe I can go faster here. Of course, there is no overlap. Right? So that would be everything outside, and that's in your pink, right? So let me write some notes here. Complement operation. What does that mean? That means everything outside. And similarly, we can probably also talk about the and the or operations. So if you have an and operation, what does that mean as far as Venn diagrams are concerned? This and this, right? So that would represent an intersection, which is what represented by like this symbol inverted U, right? That's your and operation, which we are indicating in the logic expression using a dot. And similarly, this or this, right? Like for or operation, what would it be? Union. So that is what? A U. And that is your plus, right? So now let's talk about x. We got it inside the circle. X complement, we shaded everything outside the circle. Now we need to do a union, right? Because there's a plus. So we got to do this or this. So x union x complement. So what should that be? Well, everything shaded, right? The whole the whole universal set is now shaded for the left hand side. Now let's do the right hand side. Right hand side is what? 1. 1 where? Everywhere, right? And then once you finish shading, all you do is look at the shaded parts for both left hand side and right hand side, and clearly they are exactly shaded in the same spaces, right? Blue union pink is the same as this yellow. So that's how you prove things using Venn diagrams. And it works really well here because the binary variables have only two states, low and high. Venn diagrams also have two states, shaded regions and unshaded regions. Okay, questions here? Now let's also talk about 5D, right? What would be 5D? X would remain as is, or would become and, X complement would remain as is, and the right hand side goes to 0, right? I too likes tea and ice cream in the union. That was meant for someone else, Knife. You got to keep track of who you are texting the message to. Alright, so X and X complement equals 0. Don't leave. He didn't get your joke. I didn't get it. What was the joke? How are things really? I see union. Okay, so we are talking about union for the OR operation. Where did sushi and ice cream come from? Yeah, RPI union. Yeah, I got that. But all right, now I wanted to color code it, guys. That's why I did the pink and the blue. All right. Let's all right, here we are talking about 5D, right? X and X complement equals 0. That's what we are trying to see, whether we need to kind of maybe with this example itself we can prove 5D. So when you're looking at X and X complement, you're essentially saying everything inside X, does it have any intersection with everything outside X, right? Clearly everything inside X intersection everything outside X, it is going to be a null space, right? So that's 0. So using Venn diagrams, you can quickly prove 5D in the similar manner that we did over here, or you could do perfect induction here, right? So you can say X is 0, run through this. Y is X is 1, run through this. And the thing is, if X is 0, this guy will make it false. And if X is 1, then this guy will make it false. So I don't think we need to prove 5D explicitly anymore. So we can move to property number 6. So let's see what is property number 6. Oh, we have run out of properties here. Oh, there it is. So property 6, commutative law. All right, X or X equals Y or X. This is a classic example of a Boolean algebra property being the same as the arithmetic algebra property, right? And the same applies for this guy. If it was arithmetic algebra, addition is commutative, or operation turns out is also commutative, and operation also turns out to be commutative. So X or Y equals Y or X. Let's try to do this in some way. Where do I do it? Maybe I do it after this. So property number 6, commutative. What is that? Order doesn't matter, right? Simple. That's it. So let's see. We have X or Y on the left hand side, and on the right hand side we have Y or X. Now, if you were doing this using perfect induction or the truth table method, you'll probably have a pretty easy time doing this, because you will say a variable x, a variable y, one column for x or y, another column for y or x, right? And because you have two variable situation over here, we have four possibilities to consider. So when you do x or y, you are essentially doing the operation in this order, right? 0 or 1, 1 or 0, 1 or 1, right? This and that, this or that. So what would that result in? Well, over here, it would result in a 0 here, a 1 here, a 1 here, a 1 here. But if you switch this around and you do y or x, this or this, this or this, this or this, this or this, you would get exactly the same. 0, 1, 1, 1. So you can clearly see that this particular column matches this column, which proves this property using perfect induction method. Now, a quick question. Do all entries have to match, all four of them? Or can 3 be the same and 1 be different and we still prove it? All have to match, right? So in the perfect induction or truth table method, and no matter what you're looking at, only if all conditions satisfy, only then you can say the law is proved, right? Only if one of them breaks it, then you don't have a proof. So you have to match all entries. How about the other one, the Venn diagram way of doing it? Well, you would start off with a universal space. Let's do that for left hand side. Let's do this for right hand side. LH, oh, come on. Right hand side over here. I have to draw 4 circles here, right? So let's see. One here. Better. 1, 2, right? So for my left hand side, this is x, this is y. For my right hand side, this is x, this is y. So if I'm going to do the left hand side first, and for my left hand side, what do I have? X first. Where is x? Inside x. All of that is x. For y, all of that is y. X or y, it would be the union of both of these combined, right? Now, if hypothetically, if we were doing x and y, which region would that be? You've got yellow, you've got blue, the intersection is just in the middle, which turns out to be green color, right? That's just like, it's not part of our proof here, but I just want to mention that that's what you would take that from. But in this case, we have a union. So yellow plus blue is what you have for the left hand side. How about for the right hand side? Well, we are just doing things in a different order, right? So let's do y first. So that would be this. And then you would find the union of y with x. For x, maybe I use a different color, a brown. And as you can see, we are doing a union here, right? In fact, we are doing the union for both these things. So all the shaded parts is what we are comparing. So whatever shaded part you have over here is the same as whatever shaded part you have here, over there. So that's how you could prove a property using Venn diagrams as well as your truth table or the Boolean algebra, perfect induction method. All right, let's keep pushing through here. Oh, sorry, I need to look at the next property. 6D. I think that's just the intersection, right? So let me take this, copy it, paste it after. What all do I need to change? I need to change this to 6D. This operation I need to change, that operation I need to change. What else? This is 6D, this is AND, this is AND. Everything remains as is, but now because you are doing the intersection, what would change? Well, you are looking at this now. And over here, you are also looking at the intersection. You guys see that? So they match, right? This intersection matches that intersection. So you are essentially comparing the result of the sort of all right, so here we are looking for intersection. Now I want to tie this to some interesting things you could do with a truth table and a Venn diagram. So let's do an exercise here. I'll have a two variable truth table. So I'll have x, I'll have y, right? So I can have x is 0, y is 0, 0 and 1, 1 and 0, and 1 and 1. For each of these combinations, I will write their corresponding term that makes them 1, right? So which logic function would take these two as 0 and make it into a true output? So the input should be 0 and 0, the output should be true. Which logic function allows you to do that? NOR, right? So NOR does it, but I'm going to write NOR in a different manner. I'm going to write that as x complement and y complement, which is the same as NOR. Right? You guys agree with that? X complement ANDed with x complement, you get 1 and 1. That's the way you get your true. How about the next one? You have x complement De Morgan's. Yes, that's your De Morgan's law. For the next one, what should I write? X complement and y. Next one, x and y complement. And the last one, x and y. Right? You guys see that? Now, what I'm trying to do here is, I'm trying to relate those four things to a Venn diagram. Fragments in the Venn diagram specifically. So I'm going to erase this and this. I'm going to draw two circles here. One for x, one for y. How many fragments do I have here? Four fragments, right? And each of those fragments is actually mapping to one of these terms, product terms, ANDed terms. So let's try to relate which one is connected to which one. I'm going to put a barrier in the middle so that you guys see this as two separate things that are happening. So I'm going to erase this guy. Yellow. All right. Where does this fragment go? X complement and y complement. That is fragment 1. How about the second one? X complement and y. Where is that? 4 is right. Right? 4 is right. So you see, everything outside x intersection with y. Right? So everything outside x intersection with y. So that would be here. Right? So that's your 4. Next, x and y complement. That would be fragment. Which one? X intersection with everything outside of y. That would be 2. Perfect. And there is no surprise here. The last one is going to be our fragment 3, which is x and y. Intersection between x and y is right here. You see that? So each term that you see over here that makes it 1 is actually corresponding to a particular fragment in the Venn diagram space. Now let's make it a little bit more interesting to just check whether this holds up with 3 variables or not. So with 3 variables, how many circles should I draw? Well, you have 3 variables, so you should draw 3 circles. 1, 2, 3. And when you have that, the x here, y here, z here, how many fragments should I well, we are going to go up to a 2-dimensional figure of 3 variables with Venn diagrams. I'm going to stop at 3. All right. So with x, y, and z, how many fragments do I have? Clearly with 2 variables, I had 4 fragments, right? So with 3 variables, I should have 8 fragments. Let's just identify them. I will write their number here, and this numbering scheme is just to count them. This has nothing to do with their particular logic expression. So I've got 1 here, 2, 3, 4, 5, 6, 7. Am I missing something? Yes. You see that? So now using this, can you guys tell me what is fragment 3? Which particular AND term is being represented by fragment 3? It has to be an ANDed term. So this and this and this. It has to include all literals, x, y, and z. So Jeremy says, so everybody is sort of saying the same thing, right? Let's try to see. So I have to be in y, but I have to be outside of z, and I have to be outside of x, right? So x outside of x, y inside of y, and outside of z. So fragment 3 essentially is representing that. Do I see that? And if you extend this, you can actually find the product term for each one of these. For example, 6 would be x and y and z, right? You could do all of that. And now here is the interesting thing. You can say 6, fragment number 6 or fragment number 8 will give me x and y, right? So here, what is the term for 6? You guys agree with that? X, Y, Z. All right. What about 8? So between x and y, but outside z, right? You guys see that? X and y. Sorry, I wrote it wrong. X and y, but outside z. You guys see that? That would be for 8. But if you do 6 or 8, what do you get? Well, if you use logic expressions, you get x and y and z, or x and y and z complement. But because we know that this or this should be what? X and y, right? So you see, these two combined shades this part. So what is that? Well, that is an intersection between x and y. It doesn't matter what z is, right? So we kind of used Venn diagrams here to do some logic simplification, right? So we took a logic function here, we simplified it down to x and y. And if you notice closely, the variable that changes gets eliminated, right? So it all ties to, yeah, that's right. It all ties to where we are going with this, right? Eventually to K-maps, yeah. All right, so we're gonna have a lot of fun with this, but I hope you see that with Venn diagrams, each fragment can be used to indicate a particular product term. When I say product term, I'm talking about AND operation between two variables. Each of those variables could be in its true form, x, y, or z, or its complemented form, x complement, y complement, z complement. All right, let's come back to our properties. What were we doing? We were doing 6. We did 6. We did 60 also as well. Associative property. Now for associative, you have x, y, and z, and the associative law also says it's a 3-variable property which says order doesn't matter. So if you do x or y first, or you do y or z first, or you do x or z first, it doesn't matter. They all go to the same operation, which is x or y or z. And again, 7D is essentially saying the same thing, but for the AND operation. So OR and AND, they are both commutative as well as associative. You can actually prove 7 by saying, let me make x or y some new variable. And if you make that into a new variable, you are essentially borrowing 6 to prove 7, right? So you could do that. Let's try to prove associative property over here. 6, we did 60, we did talked about that, and add a page here. How are we doing on time? 3:40. Let's do associative quickly. So we have x or y or z, in which case, the first case, I am going to do the OR of x or y first. In the second case, I'm going to do y or z. And in the last case, I have x or y or z. So what is the proof here? Again, you can use Venn diagrams to do this. Let me try to save some time. Try to do it using the perfect induction method. So what I'll do is I'll have 3 input variables here, x, y, or z, x, y, and z. First, I'll evaluate y or z, x or y. Then I will try to evaluate x or y, then z. In the next one, I can evaluate y or z. And last, say, I can do x or y or z. So how many things am I going to have? X, y, and z. I'm going to have 8 combinations between them. So let me work through this truth table in a very systematic manner. I'm going to go z is 0, 1, 0, 1, 0, 1, 0, 1. Y is 2 zeros, 2 ones, 2 zeros, 2 ones. And x is 4 zeros and 4 ones. The first column that I need to evaluate here is x or y. All right, so I'm looking at this column, and I'm doing an OR operation between them. Now, if I notice x and y, the first two are kind of 0, but everything else has a 1, right? Somewhere or the other. So I can evaluate that simply by saying this is going to be, first two will be 0, and the rest of them should be working out to be a 1. Next, the next column that I need to evaluate is x or y, whatever that is over here, and I need to OR that with z, right? So this column or this column. Well, all of these are already 1, so I don't need to worry about that. This guy is 1 over here, so I can include that over here. Only the first remains to be 0. Only the first guy is 0, everything else is a 1. 1, 2, 3, 1, 2, 2, 2. In the same manner, I can do y or z first. So what happens to y or z? It looks like 1. So the first one is 0. 1, 1, 1. Okay, this guy is 0. So I got a 0 there, and then I got 3 1s. Then I got a 0 next, and I got 3 1s again. Right? And then the last one, when you add or x at the end, what happens? You see, this 0, because of this 1, it's going to have a 1 in that column. The first one remains to be 0. So 0 followed by all 1s. And if you see at the end, this column here matches that column there. So at least that proves kind of half of this, right? Now, if you want to put a column for x or y or z, you can have this or this or this, and you can see that all the bottom 7 entries are going to give you a 1. Only the first one is going to give you a 0, which matches the columns that are highlighted in pink. So that proves those. Let me just highlight this guy and say that this is changing because of that. And then this changed. That changed because of that. All right. How are we doing? Questions? (7D) x y z x y z x y z. Do x and y first, or this first, the same thing as that. So this is again similar proof, can be done using Venn diagrams, can be done using truth table method. I'm hoping that you guys are seeing this pretty clearly now. All right, so let's move on to 8. What is 8? 8 is distributive law. All right, so what is the law itself? Let's write it down. X and y or z, I can distribute exactly the same way as you would distribute in arithmetic algebra. So you would do x and y or x and z. It's a very useful property to have because this will help you convert things to like a sum of products form. This is called a SOP form, sum of products. So product 1, product 2, they are both summed together. So we'll take a look at all that nomenclature slightly later, but distributive law is something that you use a lot. So let's try to prove this distributive law using maybe a Venn diagram. So let me use black, and then I need 3 circles. Gonna name them X, Y, and Z. So for the first one, that's my left hand side, and I need to do the same thing for right hand side. Left hand side, right hand side. What do I have on the left hand side? I'm going to do X or Y first, right? Indicated by parentheses. I'm going to do X or Y first. So where should I shade for X or Y? Well, that's pretty simple. All of Y union all of Z. Right, so that's your X or Y or Z. Right. Now I need to find the intersection of this space with X. So where is that? is simply going to be here. You see that? So that's your left hand side. So the blue shaded part, the blue lines, is kind of what I'm monitoring here. That's essentially my outcome for the left hand side. Not the pink one, but the blue shaded part, the blue lines. Next, on the right hand side, what do I have? I have x and y union x and z. Alright, so because it's union, I can just keep on accumulating lines one on top of other. So if I'm trying to do x and y first, where should I do this? Well, for x and y, I'm essentially looking at the intersection here between x and y. That's your x and y. Union x and z. Where is x and z? Right here. And when you do the union, you are essentially saying all the shaded space here. Now you compare the blue lines here, no matter how they look like, right? It's union. They match the same fragments that are shaded on the left hand side. So that would prove the property there, the distributive law. Again, you can follow the same sort of way to do the other one. 8D. You think it is useful to indicate the fragments here? Let's do that. Wow. Okay. X, Y, and Z. Now, what I'll do is I will try to list out all the product terms first between X, Y, and Z. X, Y, Z. X, Y, Z. X, Y, Z. So I've got 4 of them here. I'm just going to copy paste that so that I get 4 more, because in total I need to look at 8 possibilities. What I'll do next is I will put AND between them, because I'm trying to make them one by either inverting the variable or not inverting the variable. Next, I'm going to follow the sequence of 0 to 7. So what is 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and then 1, 1, 1. Right? So I've got 8 unique product terms between X, Y, and Z listed over here. And my claim is that each of these guys are going to correspond to a particular fragment in the Venn diagram space. So this is what? This is 0, 1, 2, 3, 4, 5, 6, 7. So let's try to number them and map those 0 through 7 values on the Venn diagram. So what do I have? Outside X, outside Y, outside Z, intersection. That would be 0. Now if you did this outside X, outside Y, and Z, that would be 1 here. And if you keep doing this, there will be 2 there. 3 will come out here. 4 will go there. 5 will go here. Then 6 and 7. And you can check this later on. But that's what those map to. 8 unique fragments in the Venn diagram space for the 3 variable situation, mapped to 8 unique product terms between X, Y, and Z, in which each literal x, y, and z either appears in true form, such as x, y, or z, or complemented form, such as x complement, y complement, z complement. Okay, let's do 8D after 8D. Now, a different twist here for 8D. Property first, I'm going to say it is x or y and z equals x or y and x or z. So this is the property HD, associative law, but the dual of associative law, 8. And in this case, what I'll do is I'll try to prove this using other Boolean algebra properties. Using other BA properties. So let's take a look. The common approach to going about this using Boolean algebra properties is, one option is you start with your left hand side, manipulate using Boolean algebra properties to go to the right hand side. That's one way of doing it. Or vice versa. Start with the right hand side, manipulate the expression to go to the left hand side. Both should be maybe slightly different. One way might prove to be easier than the other way. So let's try to take a look at what you would do in this case, right? Would you start with the left hand side and try to go to the right hand side in this case, or would you do the other way? Where would you start, left or right? Right to left, for me, it looks a little bit easier. Jeremy says I'm going to start with left. Sure, it's up to down. Yeah. So if I do right to left, you see this is in a very nice distribution ready, right? Like I could distribute x or y onto each of these terms, x or z, and then I can start simplifying things. If I start from left and I want to go to the right, that would require a little bit more creativity, which is okay. I'm just saying that one way tends to be a little bit easier. The other way, most likely, you're going to put in some, you're going to have to be a little bit more creative. So I'm going to start with right hand side here. For this one, factoring x or looks quicker. Yeah, so again, it would depend on the operations that you are most comfortable with. For some students, one way might be better than the other. I'm just saying that for this case, I see going from left to right to be a little bit more, requiring you to put that extra thought than from right to left. We'll do both ways. I'm just saying for this case, I'm going to do with right hand side. So let's do right hand side. What do I have? I have x or y ANDed with x or z, right? So I have two terms ANDed with two more terms. So when I open this up, when I distribute it, I'm going to get 4 terms out of this, right? So like FOIL, right? So x and x and z, y and x, y and z. So let me write those down here. I've got x and x, or x and z, or y and x, or y and z, right? So those 4 things I'm going to get using FOIL. What can I do after that? X and x, well, that is simply x, right? Don't need to worry about that because of 3D, the dual of idempotent law. X and x is x. X and z, well, can't do anything about that. X and z remains as is for now. Y and x, yeah, can't do anything about that either. I'm going to, well, I can use 6t to write x, y and x as x and y, thing 6D here, and then I have y and z at the end. Right. Now I see x that is alone, right? I like that. The reason is x appears over here and x appears over here. And because it is by itself over here using absorption, yes, what you can do is you can pull out that x, factor of x, from the first 3 terms. Factor out x. You are going to get 1 or z or y. And then you will have at the end y and z as is. The moment you have 1 or anything, you know it is going to be 1, right? So you know that this should go to 1. So you have x and 1 or y and z, which should go to x or y and z, which is your left hand side, which is the proof, right? So from here to here we used 1D. I mean x or x and z is x. Yes, absolutely. You can pull out x, the first term and the second term. You have got 1 or z. 1 or z is 1. So you're left with x. But you know, I'm not going to stop here. I can try to get away with this too, right? I can also include that over here because that also has x. So the more number of terms I try to combine or factor in this case, the more number of terms I'll get rid of, right? So I'm trying to simplify it in a manner that eventually leads me to that. I only have to be careful about this. I cannot logically break my proof. That's it. Like I have to be logically be consistent. That's all. All right. Let's move on to the next property after sure. Now, you know, I'm just looking at these properties from the table here. I just don't want to spend time going back and forth between the slides. So this is 9. The property number 9 is x and y or x and y complement equals x. We have seen this before, right? Where have we seen this before? Something similar to this. The variable that change, that it gets eliminated, right? So I know that it has to be, it has to get proved, like it is accurate. Let's prove it. Let's prove it using Boolean algebra. Adjacency, yes. And adjacency is what we are going to leverage to, you know, do Boolean algebra. We are going to use that for simplification. We are going to use that for K-maps. We are going to see a lot of adjacency benefit us to simplify expressions. Everything, almost everything in terms of simplification is going to be based off of adjacency. Let's see, what are we trying to prove? This 9, right? So let's start with, you see, here is a classic example, right? If I started with right hand side and tried to manipulate it, it is going to require some creativity. But if I started with left hand side, I can try to you know, pull out an x. What am I going to be left with? Y or y complement. That should combine to give me 1. Then I'm left with x, right? So you can formulate a plan to go through that proof in your head when you start with left hand side, a lot more easier than if you started with right hand side to go to the left hand side. You're going to have to manipulate things. So for example, what I mean by manipulating things is sometimes while you're doing mathematical like arithmetic algebra, you sometimes add and subtract 1, or you know, add and subtract 0, or multiply and divide by 1, or multiply and divide by a constant. So all those things you're doing there is essentially helping you to work through the manipulation, right? So That's what you're going to have to do. You're going to have to change x without logically changing it. You have to kind of go here, right? And there is a way to do that as well, which is, I'll talk about those tricks as we go on. But over here, I'm going to take my left-hand side and I'm going to say x is the common factor between the first two terms. I'm left with y or y complement, which is 1. So this should be x, which is my right hand. And in fact, you could go the other way by forcing the missing literal. Like if you force the missing literal on x, you actually go to the left hand side. So there is a way to prove it the other way. More about that in a little bit, but I'm going to write the statement that we are going to see play out a lot here, which is the variable that changed got eliminated. So I hope you guys remember this as we go on. Next, what do I have? I have 9D, right? So for 9D, x or y ANDed with x or y complement equals x. That's the property. So again, now I can start with my left hand side and I go to my right hand side or the other way, but starting with left hand side is probably a lot easier. So let me work through that here. ANDed with this, which is x and x, or x and y complement, or y and x, or y and y complement, right? X and x is x. X and y complement, can't do anything about that. Y and x can be written as x and y. How about the last one? Y and y complement. What happens there? That goes to 0, right? Sure, yes. So I've got a 0 there. Next step, x or x complement and x or x and y complement, or x and y. All of them have x. So let's pull it out. Factor it out. I've got 1 or y complement or y. All right. 0 goes out, right? X or 0 is x. So I don't even need to write that or 0. All of this is 1. So x and 1 equals x should be your right side. So hopefully that proof was okay. Next, I want to keep moving here to property number. I want to get to a place and leave you with some interesting proof, so that can be a good end of the week. All right, so 10 is what? 10 is x or x and y equals x. That's your property number 10, or the absorption property. So what is that? You start with left hand side. All right, what is that? X or x and y. Okay, you see an x in both terms, pull it out, factor it out. You've got 1 or y, which is x and 1, which is x, which is your right hand side. Pretty straightforward. Nothing to be concerned of. And any one of these properties can also be proved using other ways, right? The perfect induction or the truth table and the Venn diagram. All of that is possible. Those, now I'm hoping that those are a lot easier for you than the Boolean algebra way of doing things. 10D. X and x or y equals x. Okay, how do I prove that? Well, I can start with my left hand side. I'm going to get x and x or x and y. X and x is going to be x, and I'm going to get x and y, and this is actually just x because of property number 10. So pretty straightforward to look at 10. Let's look at 11. We are getting close to some interesting proofs here. X or y complement ANDed with y equals x and y. That's the property. and the proof is left hand side. I'm gonna do that left hand side, starting with left hand side. What am I gonna have? If I distribute it, I'm gonna get x and y first, then I'm going to get y and y complement for next. This is x and y or 0, which is x and y, which is right hand side. So I am okay over here, right? So I hope that 11 is straightforward. Now for 11D, that is a little bit interesting. So I'm going to take a new slide here and I'm going to write the property over here. X and y complement or y equals x or y. That's the property, right? And it's the reason why I say it's interesting is because using this, I can actually give you guys a few strategies that you can use to either prove or simplify or verify a Boolean equations or properties. So what I'm going to do is I'm going to start, and the reason why I'm using this is because it's not very clear, right? Like it's not very clear to see. I need to take this and I need to find a way to eliminate this guy, right, to get to this, because x is x, r is r, y is y, right? So the only difference is I need to be able to eliminate this guy from here. So yeah, I'm gonna try to do that. While I'm trying to do this, I'm also focusing on giving you guys some tricks that you could use for other situations. Now, a disclaimer first. When I'm working through this proof, it is not the only way to prove this. There are other ways of proving this. The way I'm doing this is the way it is going to be because I'm trying to convey those skills to you guys. All right, so I'm gonna start with left hand side. I have what? X and y complement or y, right? Now, if you see x and y complement or y, what are the literals in this example? What are the literals in this equation? We have only two literals, right? Variables that are involved. What are the variables that are involved here? It's a two variable situation. The variables are x and y, right? There are two variables in this 11 property. Now, this particular term, the first one, has x and it also has y. So both variables are represented either in true form or in the complemented form in the first term. So fine, I'm going to leave it as is. But if I look at the second term here, I actually am missing x from this, right? So what I'm going to do is I'm going to use this trick of force the missing literal, so that we can combine. So that's a trick that I'm going to use. Something like multiplying it by 1. If you multiply things by 1, you don't change the value, right? Like in arithmetic algebra. So what is multiplying by 1 translate into Boolean algebra? What does that translate to? Multiplying by 1. ANDing with 1. Absolute. So ANDing with 1 doesn't change the value. Sure. But I need to AND 1 in such a way that I'm forcing the missing literal, right? Okay. Is there a way to do that? And x when x complement. Yes, that's right. So I didn't change the value logically. I just forced the missing literal. So what is this going to result in? It's going to result in x and y complement, x and y, x complement and y, right? Okay. Now what do I do? Now these two guys have, I'm going to start looking to combine things, right? Could you also, or with, oh yeah, absolutely, Andrew. So the disclaimer I mentioned was because of that, like that you can OR with 0, you can AND with 1. There might be other ways of going through this proof, but I want to like touch on these key tricks that you could use in other more complicated examples. So I want to use this 11D to look at that. Let's see, what 6. Okay, so let's see. I have x and y complement, then I have x and y, then I have x complement and y. All right, so I really don't know what to do here, because I actually made my life a little bit more complicated. I wanted to go from here to here, but I actually made it more complex. So the next, yeah, what Andrew said, could you also OR with 0? Yes, you could. I'm just not doing it in this example. There are other ways of doing it. You could OR with 0. You could find other ways of proving this property as well. The second trick that I want to mention is you can duplicate terms to combine more. Why is that? Well, x or x is x, right? So I can duplicate x as many number of times as I want, and my only purpose of duplicating things is so that I can absorb them into other terms. I can combine with other terms. So which term am I going to use? Now that can be a little bit tricky. So I'm going to use x and y as the term that I duplicate. And you will see in a minute why I chose that. So let's see. I have x and y complement, and instead of writing one term which is x and y, I'm actually going to write x and y twice. And then the last x complement, oh sorry, not equal, plus. The last term x and y, x complement and y remains as it. Now hopefully you see, once this is duplicated into two terms, I can combine this guy with this and this guy with this, right? So if you look at the first one, what do you have? X is the common factor between them. Y is changing, so it gets eliminated, right? So x, y complement, or y, what is that? That is simply x. What about here? I have y as the thing that is common factor. So I'm going to factor it out. And I'm left with x or x complement again. This will result in simply y. So if I zoom out here, what are you left with? Well, you're left with x or y, which is your right hand side. So two things. One, you can force the missing literal so that you can combine more. And when you're forcing that missing literal, it can be with a 0, which is x and x complement. But you would have to adjust your steps, the subsequent steps accordingly based off of that. In my case, I forced the missing literal by ANDing with a 1. Right? So I ANDed with x or x complement here. After that, I duplicated the term that I could combine so that I can simplify down to my right hand side. And the term that I chose was x and y, because if I chose that, one term I could absorb in that, the other I could absorb in that. That's why I chose that term to duplicate. Now, when we go into a little bit more mature conversation about simplifying logic expressions with learning K-maps, you will see a connection. I'm going to show you the connection between Boolean algebra and K-map to exactly know which term to duplicate. So hopefully when we get there, you guys are going to have a little bit more mature understanding of how do you get that particular term. Like, is it just hit and miss? No, it's not. It's based off of a methodology. It's a very structured or a systematic procedure. Okay, so I'm gonna stop recording here.